476 millivolt in one and 500 millivolt in the other.
You said that this issue got resolved using some other technology node?
Yes, sir, that got resolved, but only when I was adding the cascode on the left hand side. Without the cascode, it's not getting resolved.
Did you check the gain at that point? When you go to that point, what is the gain?
Yes, sir, I checked. I'll just show you.
What is go back? What did you set up? Just show me the value again. Okay. How much is the input signal magnitude? What is the input signal magnitude? 0.1 millivolt. Here, what are you getting? 830 to 870. That means just around 40 millivolt. So 400 gain you are getting. $400 is not bad, but you can improve. What is the AC analysis plot? 400 means the gain of the individual stages is poor, or basically the cascode stage you need to improve the gain, GM you need to improve. So 46 dB, that means something similar to, what you are getting. So 3 dB for around 400 gain. And the cutoff frequency right now is go to that 3 dB point. So 3 dB point is so it is much higher than 10 mega. So you have enough. What is the phase margin? Phase margin is so go to 0 dB point. Phase margin anyway you can improve, but right now you have enough bandwidth. So bandwidth you can reduce and you can increase the gain. So there's a lot of room for increasing the gain. The phase is also not good. So phase is only 10 degree. So starting from, so where is the phase starting from? If you have taken from positive input, right? So phase is starting from 180 degrees. So you have taken from negative input. And then the next phase shift you are getting is almost close to 10 degrees. So phase margin is not very good. So you may have to put a cap over there, but gain magnitude you can definitely increase. So what is the size of the input device? You can increase it further, make it maybe 40. Output side, what is, let's see the output stage dimension. You can reduce the current, make the current 5 micro. Output side, show me the dimension. Go down. So you have to increase the L. So make both of these also larger. So W and L both you can increase. So W you can make it 40 micro and length you make it 90. 90 nano, not micro. You have you will have to change the mirroring. So just look at the mirroring because you have the mirroring ratio has to be maintained. So this one you have increased W and L both. Downward side you have increased W and L both. Close this. And the middle side the ratio is same. So fine. This to this ratio anyway you have not changed, and the current should be remaining similar, so this should be fine. What is the ratio between M3 and 12? That ratio I thought that is same, right? Whatever I provided. Check M12. Okay, close this. Check the plot. Do the AC plot again. So there are two multiple poles coming. You have to change the DC value. Change the DC value so that again it is you have to find out the new point. There is another way of doing this rather than changing the DC sweep, where you can also connect a large inductor in the feedback unity gain. The inductor value omega L at DC will be 0. So it will all for DC it will act like short circuit, but for higher frequency it will act as open circuit. So for that we need to put a L which is very high. Theoretically it will work just for the analysis. So it has slightly improved. So it is now coming 53 dB. So this is similar to what you have obtained earlier, right? So earlier also in that two-stage op-amp you obtained something like 56 dB. Here you are also getting something similar. You want to improve further, again, output stage you can modify, you can increase the length of the output stage. So let us try to do that. Output stage you can maybe try to increase the length further. But W and L both has to be increased, so make it 180. Input device also you can increase. No, input device length does not matter. You don't need to increase the length of the input device, only the W. Which device is this? What are you doing? I told only the input device. Which other device have you modified? M9, M10 will not be modified because that will affect the ratio of the second step. Current you can again you have to change that. You have to get the DC point. Just drop.
Yes, it has dropped.
So there must be some problem in the sizing somewhere. Check the sizing once again.
Yes, sir. This is 45 nano micro. This is 45 nano 80 micro. 41 80, 20 micro. 80, 40, 185, 40, 180. This
Or
is
the DC
20.
point is not accurately chosen. Did you check what is the DC point? Check the output DC
Yes, sir.
point.
Yes, I will show the. I'll just sweep once.
You choose a shorter range so that it is doing more accurately. Just close to that value only.
Yes, sir.
Here, no, this is not enough. If you are having very less points, so what you do is just select the intermediate, that is a smaller range, keep between 370 millivolt and 380 millivolt.
Yes, sir.
Increment, you make it even smaller. 0.1 milli.
Yes.
0.01 is also fine. Just do it more accurately.
Yes, sir. So 0.1 will be more fun. Still very sharp. P74, 78B. Yes, sir. Now it is giving a good gain. Like I'm getting 110 dB.
Yes. So 110 dB is good.
The
Look at
bandwidth
the
has degraded.
phase margin. You check. Bandwidth will definitely, once you increase the gain, bandwidth will go down. That is obvious.
10.7. Phase margin is bad, sir. Around 12 degree phase margin.
So that is okay. You have to put a cap so that you can compensate. So you put some cap, maybe 50 femtofarad. Put a cap of 50 femtofarad.
I've put, sir. It's here. It's now at 22 degrees phase margin. I think I'll need to increase the cap further.
Sorry, once again.
Sir, it's at 22 degree now, the phase margin. I think I'll need to increase the cap further, like around 100 femtofarad, I guess, or 200 femtofarad. Degree. Sir, now I'm getting almost 41 degree phase margin.
Look at the 3 dB point. And it is going very down because the gain has been increased.
Hello. So
Yes.
it has gone quite low, sir. It is around 400 hertz now.
Yes, that is expected because your gain is so high. So it is expected that the uh, bandwidth will be poor.
Yes.
So here, this is almost like even go to that DC close to origin, almost 110 dB. Not origin. Origin when it's close to DC, zero value, and then the zero frequency.
Oh, yes, sir. Started from 100 hertz, so I need to go to sweep. This is near the origin.
Yeah. So 110 dB is almost like 30K. So that gain is pretty high. Not 30K. It is coming 300K. 100 dB and 110 dB is 300K. So I think the earlier values also you might have got very good gain, but because you did not check the I think the resolution of the DC analysis should have been done properly so that you got appropriate DC. So for earlier values also, if you had done the analysis properly with higher resolution in the DC analysis, you will get the exact DC point so that the gain was higher. So this much high gain we may not be requiring unless the application demands that kind of gain. So here, if you look at, say, this is 13 10 to the power of 4 gain, which is pretty high. Generally, for this kind of even front-end amplifiers that we need, maybe at max we will need is 80 dB gain to 90 dB gain. So here, if you want to improve the bandwidth, there is a opportunity there. You can sacrifice the gain and improve the bandwidth a little bit. But for the time being, you can just try to confirm. You can do a small signal analysis. Maybe you can do a transient analysis also just to confirm So with this DC condition, maybe you can apply a very small voltage at the input, maybe 0.01 millivolt or something, and then see what is the effect. 1
Yes, sir.
microvolt. You can apply 1 microvolt.
One. Sir, 1 microvolt, it results in a peak-to-peak voltage of 200 millivolt approximately. So the gain will be, sir, around 10 to the power 5.
So peak to peak amplitude of input is how much?
Sir, 2 millivolts, sir, peak to peak. 2 microvolt. 2 microvolt.
Yeah.
And this is
So then with
200.
100. So this is 10 to the power of 5, around 10 to the
10
power
to
of
the power
5 gain.
5.
Because you have taken a higher frequency, if you go lower the frequency, it will further higher. So you can lower the frequency.
So I'll put it 100 hertz. I think it is getting clipped.
So you're clipping, that means you will need to gain it more than that.
Yes, sir.
So then you have gain is more than the output range. So gain
Yes,
is
sir.
so high that the output is clipping. Output range, it is going beyond it. So you need to reduce it further. Make it 1 millivolt peak to peak. Oh, sorry, 1 microvolt peak to peak.
So it was 1 microvolt. I'm making it 0.1 microvolt. Now, so it's around sir, around 3 into 10 to the power 5.
Yeah, so this is confirming the AC analysis. Whatever we get from the AC analysis, the same thing is coming here.
Yes, sir. And sir, what I wanted to ask is that why is it happening that I have to put the common mode voltages at different levels?
That is some anomaly with the model. So there is some issue. I think the way they have modeled the channel in modulation may be having some problem, but this is not correct. Means in actual scenario, it will be very close.
Yes, sir.
So this is showing that the systematic offset in the circuit is so big, but generally that is not the case. Systematic offset will be fraction of millivolt. We have seen that earlier also. Here somehow it is giving that kind of difference. Generally, this should not be the case. Here there is in the two parts there is good amount of asymmetry, but still the gain and the other thing is the gain of the first stage is also limited. So because of that limited gain of the first stage, it's possible that it is basically because the two paths are having asymmetry and even the gain of the second stage on the left hand side is also less. Most of the gain is coming from the output stage.
Yes,
So because most of the gain is coming from the output stage, uh, a difference in the input in the first stage, the DC level input difference, it is not translating so much to difference in small signal currents. The DC point of view, maybe the currents are the DC currents are, so look at the DC currents of M9 and M10 in this condition. What is happening?
Yes, sir.
Because here what we need is that the output should be close to the midpoint, and for that, whatever input difference you need to have to get that, we need to apply.
Sir, in M9, we are getting almost 2.7 0.27 microamperes.
M9 is
This thing.
wait a minute. M9, yeah, M9 is 0.27 microamperes.
Microamperes.
Which one is the M9?
1 minute.
Show me
sir.
that.
This one is M9, sir.
What is the current in M3?
It's so.
M9 current is very low because the DC current difference is. So basically
Sir.
here most. So this is same 5 microampere.
Yes,
but
sir.
M9 is taking very less current. That means most of the gain is coming from the M10 side. M9 side, you're not getting much gain. So
Yes,
M9
sir.
side.
So most of the current has been taken by M10, as we can see.
Yes. So that means that the gain is mostly coming from the M10 side. M9, M1 side, M9 side, it is not having much signal. And that is not good actually, because this will also mean that you're going to get good amount of common mode gain. So here it is becoming. What you can do is just try to apply the signal you have applied to the gate of M2 or M1, M2 or M1.
Sir, I have applied at the gate of both, like V1, V2.
What you will do is just apply it at the gate of M1 only and see what is the situation.
Yes, sir. So I'll put the M2 at DC bias, right?
Yes. This circuit, it does not give this kind of behavior. There is some problem with this PTM model why we are getting this kind of asymmetry, because in cadence, etc., this circuit behavior is not like this.
So we are getting again.
Similar.
Yes, sir, there is a gain of around the same thing which we applied first. What we got first.
Okay. So then, of course, you do have similar differential, like differential property, differential characteristics is coming, but bias current is a big skew, and that skew is so there is an input-output characteristics. That input-output characteristics is the DC characteristics. If I look at it, there you are getting the high gain region at a certain point where the difference is big in the DC, and the current difference is also big. Now, what is the DC current in M14? M14 current also must be very less, I guess. So just check what is the M14 current.
Yes, sir. 14, 14. So it's 1.6 micro.
And what is the M? What is this? My eyes have
M9.
become weaker. What is this numbers? M14 and what is M6?
M6. M6 is. Sir, same, sir. 1.6 micro.
So M14 and M6 currents are same, but M9 and M10 currents are very different. Is the mirroring ratio very different? M9, M10, M9. Just check the mirroring ratio. M9, M14, M10, M6.
5, 1, 10, 5, 10, 45, 10. So all the same, sir. The W by L ratio is all same.
Okay, and the lower side. So this is the M9, the M14, M6 currents are also similar.
Yes.
And as a result, M5, M7 currents should also be similar. You can just check M7, M5. Almost, of course, it will be similar only. Same values.
Yes, sir. They are the same value.
Okay, close this. Let's slide this window towards some corner. So these two currents are same. These two currents are same, and despite that, we are getting large input difference. DC point of view, there is a significant difference. And mm,
Sir, although sir M14 and M9 both are in saturation, but in any case, the current being mirrored is largely different.
Little strange, means some of these things are model, I think, inaccuracy problems. So, of course, what we have in this case, what we have is that the net difference in the net gain of the first stage is low. Only thing is it is providing a transconductance operation. So it is converting the input voltage signal into differential current signal and then sending it out. So what you can do is, let us see, just to try to analyze it a little bit further. What is the small signal current being produced? So you can look at the drain current of M1 and drain current of M14. Likewise, you can look at the drain current of M2 and drain current of M6. So how much small signal current is traveling from M1 to M14 and M2 to M6? Are they similar or are they very different? Let us look at that.
Sir, you say drain current of M14.
Yes. And source, you can say that for PMOS, you can look at the source also. Peak to peak value.
Yes, sir. It's around 62 63 picoamperes, where I have applied around 100 picoamperes.
What do you mean 100 picoamperes?
Oh, sorry, no, I mean volts, 100 0.1 microvolts.
You look at the small signal peak to peak current of M14 and M1. I need both
Yes,
of
sir.
them.
Yes, sir. M14 and M1. Sir, M1 is 12 picoamps, whereas M14 is 63 picoamps, peak to peak.
M1 is 12 picoamp and M14 is 63 picoamp.
63 picoamps.
And what about M6?
6.
So here we are trying to see the peak to peak current.
Sir, M6 is 51 picoamps.
So again, peak to peak currents in M14 and M6 are similar.
Yes,
so the magnitude of peak to peak AC signal in M14 and M5 are similar, but the DC current is also similar. But the M9, M10, here we are seeing that the DC currents are very different. And despite that, the AC signal is coming similar. This is a little bit contradictory. So there is some. So look at the small signal AC current in M9 and M10. They will
Sir,
also be
it's
having
12 picoamps in M9 and M10 both.
both M9 and M10. You are getting 12 picoamps.
Yes, sir.
So but the DC current is different, very different, right?
Yes. Yes, sir.
So the DC current are different. The gate DC currents, the peak to peak signal is same in both M9
Yes, sir.
and
Same.
M10.
Yes, sir. M9 is same.
So M9, M10, same AC current and the same AC current in M14, M5 also, but the DC current in M9, M10 being very different. The GM will depend on ID upon viewer drive. So what is the gate voltage of M9 and M10?
Yes, sir. Gate voltage.
Dimensions are same, right? M9 and M10 dimensions are same.
Yes, sir. I have to do.
Gate voltage of M9 and M10?
Yes, I have to do the DC analysis.
No, I mean, yeah, DC operating point analysis.
Yes, sir.
If you just plot it, you will get it. So the DC voltage is the average point, right? So whatever peak to peak signal you are getting, the average.
Sir, it's 974 millivolts at gates of both M9 at gates of M9 And at gate of M10, we have 852 millivolts.
So overdrive voltage is different. So overdrive
Yes, sir.
voltage of M10 is less.
Yes, sir.
Sorry, higher. Because VSG is higher. So ID upon 2ID upon V overdrive. For the same ID, the overdrive voltage of M10 is coming smaller, higher. As a result, the GM is smaller. So effectively, what we are seeing is GM of M10 is smaller than GM of M9.
Sir, but the IDs are also different, right? As we see, so the ID of
ID
M9 is
also,
different.
ID is also different. ID is also vastly different. So most of the ID is flowing through M10. So 2ID, ID is much bigger, and then V overdrive.
So ID is also higher, V overdrive is also higher. So maybe that the GM is getting compensated on both sides. Although not by that amount, but still it will be somewhat compensated, right?
there is some problem. Another thing is, can you just change the, so this should not have much effect, but the body terminal of both M1 and M2, you connect it to ground. All the NMOS body terminal, you connect to ground. It will not be connected to source.
Yes, sir. The remaining yes, things are not connected. So it's not giving much change. I've connected all the points to the ground, the body terminals to the ground of all NMOSes.
There is some problem in the model somehow, means because the small signal currents are coming similar. DC current in the two outputs, like the left hand side, right hand side, second stage is also similar, but somehow the DC point of view there is difference, and as a result, the DC currents are also similar. So M6 current, M14 current is also same. DC current is same, right? M6 and M14.
Yes, sir. They are same.
So despite difference in the VSG, the DC current is same. That may be because again this site has a different kind of channel length modulation. But I think there is
Sir,
some problem in the.
So one thing which I noticed while doing the simulation was that when I'm mirroring from a 45 nanometer length MOS to a 45 nanometer length MOS, then the mirroring is not effective. But when I'm using this 180 nanometer MOS to bias the currents, then all the currents are approaching the same value, which is why I introduced this cascode in this leftmost branch so that I can bias it using this 180 nanometer MOSFET. In
No,
that case, all
that is not required, right? So here we are getting it without it. So
yes.
why are you again mentioning that?
Sir, but the currents are not coming the same, right? But in that case, the currents, DC currents were all coming the same, all coming 5
That is because the
microamps.
loading effect will be on both sides will be similar. So the circuits are symmetric, and you're getting, the channel length modulation effect on the M6 will be same as channel length modulation effect for the M4. So the circuit become very symmetric, but that is not going to kill your phase margin issue. So phase margin will be worse because you are going to introduce two similar poles. So there is no advantage of going to this topology. So in this case,
Yes.
at least the DC behavior should have been correct. AC behavior is coming correct. The DC point of view, we are seeing that M9 and 10 current are getting skewed. That is not expected. Generally, in this circuit, we don't expect this kind of strong skew. So here, the one of the reason is that the two sides, the M14, M5 side, the for the M14, the loading effect is very different. It is just having a direct connected M5, whereas for M5, the loading effect is very different. It is having a high impedance load. So for M6, if I see M6 at the top, it is facing only, it is facing M11, M8, and M7. So if you look at the impedance phase by M6, it is almost like RO, right? So the impedance in the drain of M6 looking downward is RO.
RO.
And impedance for the M14 is 1 upon GM. DC point of view also, the M14 is facing only a single MOSFET. Of course, the VGS of this MOSFET should be decided by the current, but on the other side, it is facing three MOSFETs in it's facing three MOSFET in cascade. So 3 MOSFETs are cascaded, and then you are having a this is going to have a very different channel length modulation effect because the VDS constraint is going to be much tighter for M6. So that may be the reason in this scenario, because the output stage, the channel modulation faced by M6 is very different than the side of M14, M5. As a result, it is creating a difference in the input voltage, so that for a output voltage to be midpoint, we are requiring a significant difference in the input voltage, so that we are in the high gain region. But generally, I mean, we have not observed this kind of thing in your cadence tool. So the way lambda equations have been modeled, maybe that has been different over here. So for the time being, I guess if you want to make it more symmetric, then one possibility is that here, just like you are biasing the M8 is biased using the mirror, M7 is taking the current from this one, and likewise this guy. So if we want to bias it some other way, that would be tough. Even if you bias M7, I think this is fine. I don't think we need to change anything.
Sir, we cannot bias M7 externally, right? Because it's already coming from the M5, or otherwise it will not work like the way we did, right?
You can bias it from another mirror also. That is also possible, but you have to make sure that your the branches, M7, whatever mirroring circuit you are using from there to M7, that ratio should be symmetric, upside ratio, downside ratio. But for the time being, I don't see any major change that can be done to improve this. So this issue, I am not very sure at this point why this big difference is coming. And the only issue that I'm seeing, only reason for this that I'm seeing is the asymmetry in the right hand side output stage and the left hand side second stage constituted by M4 and M5. The M4, M5, the loading effect that M14 is facing, M14 and M5. So the loading effect faced by M14 is very different, and loading effect faced by M6 is very different. And as a result, DC point of view, if I calculate the DC currents in M6 and M14, the DC currents are coming similar, because right now we are forcing the output to be somewhere midway. We are changing the input DC condition so that the DC currents are somewhere midway. And for producing that midway DC current, we are having to increase the V in 2, right? The DC of the V in 2 is higher, or V in 1 is higher? V in 2 is higher.
Yes, sir. V in 2 is higher.
So V in 2 is higher, and that as a result is pushing more current in M10. And but if you look at the DC currents in M6 and M14, they are same. So if we now, what is the conclusion of this? So M10 is forced to have higher current so that current of M6 and M14 are matched. Because remember that the output DC point, when it will be very close to midway, when the pull up and pull down currents are same. That means M611, M11 current is the pull up current. Whatever is the current provided by M6 and M11, if that matches very closely with M8 and M7, that of course in the real condition, when you connect them together, it has to be same. But saturation region, initially what will happen if you see in the case where you're putting V in 1 equal to V in 2, what is happening there? Because the channel length modulation effect for M6 is stronger, you are having a load of 3 transistor. As a result, VDS is going to be small. The VSD of M6 is small. As a result, the channel length modulation effect is coming strongly. And then what is happening for the same gate voltage of M9 and M10, M6 is carrying lesser current, right? So when you're applying same voltages, V1, V2 at input, DC voltage is same, M9 and M10 will carry the same current, and VGS of M9 and M10 will same. And as a result, the VGS of M6 and M14 also same. But now M6 and M14, The M14 is having a larger VSD, right? Because it has only one M5. So the source to drain voltage is large for M14. Whereas for M6, the source to drain voltage is small. On the other side, M6 is having three other transistors in stack. As a result, the source to drain voltage of M6 is coming small. Despite the same VGS, the M6 is sinking. M6 is having lesser current as compared to what M7 would have. To compensate for that, the output voltage goes down so that the current in both of the branches become equated. Ultimately, it has to be same, right? M6 current has to be same as M7 current. But now, because of this condition, because of the smaller VSD, if I assume that the VDD was halfway, the VSD of M6 will be much smaller as compared to VSD of M14. Now the current in order to equate the current, we need basically the output to go further down, because if it goes down, then only the VSD of M6 and VSD of M6 will be increasing, and it will be becoming similar to the VSD of M14. That case, it will try to equate the current. That is what is happening. So that means that the channel length modulation is very significant. So here, the lambda value that you are getting is pretty large. That's what I'm expecting. So if the lambda is significant, then because of the channel length modulation, in case of V1 and V2, V1 and V2 being exactly same, M6 and M14 currents are not having similarity. They are very different because of the channel length modulation faced by M6. And then we are forced to increase V into so that now M6 current is increasing, and then the M6 current is becoming similar to the current in M14, because only then M6 and M14 current will be same, and as a result M6 and M7 current will be same, and then only it will go to midpoint. Output will go to midpoint. Is that clear to everyone? Are you able to understand the issue? So this is because of channel length modulation faced by M6 and maybe a larger channel length modulation parameter. Is this point clear? Nobody understood. Let me try to draw and explain. Anybody understood what I said? Nobody understood. Anyway, so I will try to draw and explain. But for this value, you are getting large gain. Bandwidth is poor. If we want to trade off, definitely we can sacrifice the gain and improve the bandwidth. And now using this circuit, right now we are getting almost 30K gain at DC. So if you want to reduce it a little bit, it's possible to maybe go down. So for doing that, maybe the input device, what you have, just show me the sizes. Yes, am I audible?
Yes, sir.
I don't know. Are you able to hear me?
Yes, sir.
Yes, sir.
Sir, I got disconnected, unfortunately, due to poor network.
I don't know whether other people have done anything, or they are listening or understanding, or they are just sleeping. Yes, what happened? I don't know. Means I think there is some connection problem, and who was sharing?
Hello.
Sun was sharing.
Yes, sir. Sir, I got disconnected because of the connection, sir. I'll
Are
share
you going to
again.
share again? Means I'm not able to see the screen.
Yes, sir. I'll share it again. Yes, sir. Visible, sir. Hello.
Yes. So
Yes, sir.
you can. Did you understand whatever description I gave regarding the mismatch?
Yes, sir. Yes, sir. I got it, sir.
Other people, anybody else understood? Or are you listening, or you are all of you are sleeping? Ayan Adhikari, can you unmute yourself? Let me try to do some survey.
Yes, sir.
So, did you understand what I discussed regarding the uh, difference in the input DC voltages?
Yes, sir.
What did you understand?
So, like due to this asymmetry in the circuit, there is a difference in this DC operating point, which we will get from the DC transfer characteristic. So, due to that, this there will be a difference in the DC level of the two input devices.
No, why there is a difference between the two input device DC?
So, because of the asymmetry in the circuit.
That I explained further, right? So, what is the reason for that asymmetry? Anybody else? Amresh Kumar De?
Hello.
Yes, did you understand what I discussed?
Remotely, sir.
So, what did you understand? Yeah, can you explain?
Means there is some asymmetry due to the
So the absorption capacity is very poor. Means I'm explaining certain things, and half the people, most of the people are not understanding. So I have to slow down maybe, or to use some pen paper to explain, or basically use the drawing to explain. So let me, you know, so I think at least as far as the gain concerned, he has already shown a big gain, and you have only issue is that the input required DC difference is pretty significant, and bandwidth is low. Compensation has been done to get the phase margin required. Transient value is also coming. Whatever is the AC response showing, same transient response is also coming. So these things are done. Of course, now this op amp can be used for doing useful things. But before that, I would like to reduce the gain a little bit because we may not require such a high gain. So in order to make this op amp useful for future, work, let us try to reduce the gain a little bit. So M1, M2 dimension just open. What is the M1, M2 dimension?
Yes, sir. So M1 is 80 micro by 45 nano.
You can make it 40 micro. And output side,
And
let's see the devices. Output side length is 180 right now.
yes, sir. So all of them
Not
have
bad.
180 length.
Okay, 15, 180. So you can maybe try to simulate now. You will get some reduction in the gain, not so much. Again, the DC point will change, everything will change. So the
Oh,
DC
yes, yes,
point,
yes. Yes, sir. I have to do the DC point again.
what you can do is you put a big inductor. So let us just to use a shortcut method. Let us try to put a big inductor between the output and the uh, negative input, so that you have a voltage follower kind of configuration. But the inductor value should be very high. You put it something like 10 to the power of 9 Henry, 1000 mega Henry, something like that. Or even more than that, means 10,000 mega Henry.
Sir, 10,000 mega Henry.
Yes. The reason for doing that is that for DC, it will become short circuited, but for any significant AC signal, it will be open circuit. So that means that in your AC analysis, it will ensure that the DC point is, or you can basically, rather than connecting it this way, you can also one. So yeah, that is also fine. So in terms of AC analysis, what it will do is it will just make it shorted. As a result, it will work like a voltage follower, so that V in 2 is, but the problem is that you have a DC point also. So DC point of view, when you are forcing it, V in 1 DC you will have to remove. So V in 1 DC you will have to disconnect and apply the AC signal at V in 2. That is a shortcut way, basically, rather than doing the AC analysis every time. This is just for simulation purpose. So this will basically force the DC condition to be as a voltage follower, so that the V in 1 DC is fixed to the V in 2 DC, and it is following very well. And the AC signal point of view, L1 will block any AC signal. So AC point of view, it will remain blocked. And the signal, when you apply any signal to V in 2, V in 1 will be something like an AC ground. So that point of view, you will not need to find the DC point all the time by sweeping. That is the only benefit that we are going to get. This is just for ideal case, and just trying to it's just a trick for establishing a DC point in the open circuit case, because generally the op amp will not be operated in open circuit, it will be always in feedback. So in the feedback case, this DC will automatically come. But for the open circuit case, when you have to do the open loop analysis, in advanced tools like Cadence, there are ways in which it can be done. There is the open loop analysis setup where you don't have to necessarily open the loop and fix the DC point, just like what we are doing here. But here that this feature is not available. So this is an alternate trick just to basically avoid that DC sweep. So
maybe some problem is occurring.
So what is the DC of, did you remove the V in 1 DC?
Yes, sir, I removed the V in 1 DC. It's purely an AC signal now.
No, you remove that signal also. There is no signal at V in 1.
Okay, sir, I'll remove all signals then. I'll just delete this. Not working.
And the AC signal is applied as the V in 2.
Yes, sir. Sir, V in 2 will have a DC offset, right?
No, you put whatever DC, so you put close to VDD by 2.
Okay, sir.
So what we are trying to do is we are trying to put it in voltage follower configuration. As far as DC is concerned, for DC omega L is 0. So it is like a voltage follower for the DC. So whatever is the output voltage, it should automatically develop. It should be equal to the negative terminal voltage. Or you can do the DC analysis also and try to find out what is the DC voltage is coming. This is just a trick. I mean, there is generally we don't use this in Cadence. In this particular tool, that feature is not there. That's why we are using it. So open loop analysis, the way you are doing right now, it is requiring a STB, it is requiring a DC point calculation. First, you are trying to find out what is the appropriate input DC level so that the output is at the midpoint, and then doing the AC analysis. But using this approach, so you're not getting actually. So the DC point of view, just look at the DC voltages at different points. What is the DC at V in 2?
Yes, sir. Just a minute. I'll simulate the DC operating point. Sir, at V2, I've put the DC voltage as 0.5 volt.
And what is coming at the gate of M1?
Yes, sir. Yes, sir. At the gate of M1, we have something like this, around 482 millivolts. Same thing.
Okay.
Around.
Same thing means whatever you were getting earlier.
Yes, sir. Yes, sir.
Yes. So the same will be at the output also. The output you will also get similar.
Output is also same following this.
Yeah. So as we expected, the inductor is going to be shorted at DC. As a result, the DC point of view, it is acting like a voltage follower. But there is a difference between the two sides. Now, if you look at the current conditions, that will also be similar. So whatever current you are applying at earlier, whatever current we saw in M9 and M10, you will get similar. So just check the DC current in M9 and M10.
Yes, sir. No, sir, it's still coming different in M9 and M10.
That's what I'm saying. Whatever you were getting earlier, the same thing will come.
Yes, sir. Means what we got in the earlier case, that value came, exactly that thing came.
The same value is coming, right?
Yes, sir.
That is expected because we have converted into voltage follower configuration. Now for AC, it is not giving any gain. That is surprising. So close this and apply here. The problem is that the AC signal, the bandwidth is very poor, and that's why we are probably not getting, because for lower, what you do is increase the inductor magnitude further.
So still higher.
Because what is happening, maybe the AC signal, because bandwidth itself is very poor. So AC point of view, we have to see. So now you do the AC analysis.
Is giving unity gain 0 dB.
It's not 0 dB. It is that green curve, which is 8 dB around.
No, sir, it's my 14 micro dB. And just see.
Okay, so here that means the AC point of view, omega L, right? So I was expecting that even for small frequencies, omega L, the impedance will be very high and it will act like open circuit, but that is not happening. And we are, so that means it is 0 dB gain. That means you are getting unity gain. Unity gain is not expected here because L will be open circuit, but that has not happened. You have a
So
C.
maybe if we change the DC bias of V into.
No, the DC bias is already whatever you have, so it is automatically coming. So that's the reason why we use L1, so that we don't have to check the DC bias condition. But this is AC point of view. I was expecting that it will act like an open circuit and it will give you the gain, but that is not happening. DC it is coming properly, but the AC gain is gone, and that's why we had put large L so that the AC we get it blocked, and from V into to the output we get good gain. But that did not happen. So maybe you let me think. Maybe put a small resistance in series with L1. Maybe put some resistance, maybe 1 ohm, something like that. That should also not create much difference.
No, sir, no difference.
And LC, C is here. So can we, the DC gain, AC point of view, shorted, circuited, but still not getting basically. Output DC, you check, output DC is coming properly. Output DC anyway we saw, so that was coming properly.
Yeah.
But AC gain is not coming. So although it is ideal L, and omega L should be very high. Even for 100 hertz, omega L is very high, but that's not coming.
Sir, I've increased it already to 1 kilohertz. Still, it's not.
Maybe you can just do one transient simulation, apply a sinusoid at the input V into and see, just like earlier you were doing a very small signal.
Yes, sir. I've applied a sinusoid at V into. Matrix. So it is saying that there must be some singular matrix.
It is not able to simulate, so you leave it. So this simulator having some problem. So
Sir, one thing is that is this capacitor getting any problems, sir? Because this inductor is there and then this capacitor maybe, I don't know.
that should not have been the issue. So capacitor, even if you remove it, I don't
No,
think it
it's-
will resolve.
No, sir, it's not. It's still giving failure.
We leave this for the time being. In this tool, we have to stick to that same approach where you find out the DC appropriately and then apply the signal. So right now, you are getting proper, gain. So you are all set. And the only thing is, this kind of high gain we will not be requiring. And here 300K gain was coming, which is also a little surprising. I was not expecting this kind of gain. I was expecting maybe something like of the order of 10K, means something like 30K, 40K, but it is 300K. So we have some margin. We can reduce the gain also by factor of 10x. Then also we will have good enough resolution. So how much gain to have? It depends upon many things. It depends upon the target precision. It depends upon like if you want to have a very high precision gain in the amplifier. You remember that if you make a feedback amplifier, the open loop gain plays a role, right? So ideal gain is just given by 1 upon beta in the feedback amplifier, but it is having a factor of 1 plus A naught beta divided by 1 plus A naught beta something. So that A naught beta, if this A naught beta is much higher than 1, that means A naught is much higher than 1 upon beta, then you get more and more accurate result. So here A naught is much higher than 1 upon beta. A naught is, your A naught that you have is 300K. So here, even if you want to have, say, closed loop gain of, say, even 1,000, even a closed loop gain of 1,000 can be achievable here. So we will discuss that part a little later, that, how to decide the op-amps, open loop gain, etc. But before we proceed further, I will discuss some more things, maybe something regarding the output stage and the output impedance, buffering of the op-amp. So let us stop recording here. I will start recording again, and then I will discuss some theory part. Also, I will discuss some people, or majority of the people did not understand this mismatch issue. So I will explain that on, on the board as well. So let me stop the recording, otherwise it will become too big. Stop recording.